Hello everyone, my name is Jake Hawkins, and for my final project I chose to model a self-landing rocket. So why would someone want to make a self-landing rocket? First off, if you can make a rocket reusable, you can make it cheaper than a disposable rocket. For example, the SpaceX Falcon 9 is about half the cost of the nearest competitor in its class. Additionally, if you can reuse some of your rockets, you can maintain a quicker launch schedule. For example, the Falcon 9 recently passed the Atlas V in the number of launches it has undergone, even though the Atlas V has been flying for approximately twice as long. Finally, when we decide to send humans to Mars, the easiest way to get them to the surface is to land them via a vertically landing rocket. So this is a skill that we should be learning now. Two examples of self-landing rockets today are the Blue Origin New Glenn, which is shown on the left, and the SpaceX Falcon series of rockets, which is shown on the right. I initially wanted to model a rocket that could rotate around all three axes and move in all three dimensions. However, after starting to derive the equations of motion for this system using MATLAB and the Lagrangian approach, I arrived at this very, very ugly equation. So I decided it would be best to instead model the system as a planar system, so the rocket could move in x and z and rotate around theta. As you can see, that sort of system would look like this. So this rocket has two main engines located near the bottom, which are represented by FT1 and FT2. And it also has two RCS thrusters, which are located near the top of the rocket, which are represented by FT3 and FT4. Initially, I didn't have the RCS thrusters in my design, but through the course of my testing, I found that including the RCS thrusters made the rocket a lot easier to control, because the engines near the bottom of the rocket do not provide that much torque and can't provide enough control over theta. From that picture, the equations of motion were solved using the Lagrangian and were then implemented in MATLAB, as shown here. In order to control the rocket, I decided to implement a state space system, the first of which is shown here. This controller actually only looks at the theta and theta dot of the system in order to control the orientation of the rocket on its way down. So this controller starts off the simulation, and then at a certain height it will hand over control to a different controller that will actually take care of the speed as it gets closer to the ground. The controller that actually lands the rocket is shown here. The only difference with the previous controller is that it has a slightly different Q and R matrix that leads to a slightly different K matrix in order to control the rocket as it lands. It also includes reference tracking in Z so that the trajectory of the rocket can be better chosen so that it doesn't crash into the ground and instead slowly touches down. I thought that tuning the Q and R matrices for this part of the problem was the most interesting part because it was kind of like a puzzle to slowly tune the parameters and find the exact combination that worked over the widest array of circumstances. This picture shows how the system was actually implemented in CopeliaSim. On the left of the screen, there are the different sensors that the rocket uses. The easiest to use are the GPS and the gyroscope, which are just located in the center of the rocket, and the GPS gets the Z and X locations of the rocket, and the gyroscope gets the theta dot of the rocket. The X and Z data is also used to estimate X dot and Z dot. By recording the previous time step, X and Z, the program is able to find the difference between the current time step and the last time step, and then divide by the size of the time step to get an estimate for X dot and Z dot. The two proximity sensors are then used to get a value for theta. The proximity sensors are able to measure a point along ground, not necessarily right below the rocket. This, combined with the knowledge of Z, allows us to find the value of theta. Also, as you can see, the CAD for the rocket is just a simple cylinder. This was probably the most difficult part of the project because I was trying to import different CADs to more accurately model the rocket. However, doing that kind of messed with how CopeliaSim recorded the reference frames of the rocket, and so it was just easier to go with a simple cylinder, even though it's not necessarily entirely accurate to the system. The first case we will look at is when the rocket starts with 0 theta. In this case, the rocket has no problem landing on the ground. In the next case, the rocket starts with a theta of 5 degrees, and it still is able to easily reach the ground. However, it does have to do a little bit more work to correct for theta at the end. In the next case, the rocket starts with a theta of 10 degrees. This one is a little bit closer as the rocket nearly tips over at the end, but it is still able to correct for theta and land gently, and now we'll see it just barely be able to rock back. The last case we'll look at is when the rocket starts with a theta of 15 degrees. In this case, the rocket will actually crash. It does not have quite enough control to completely cancel out theta, and as you can see, it tips past the point of no return. So the rocket can land at any angle up to about 10 to 15 degrees. In order to improve this performance, more work would need to be done to finely tune the K-matrix to improve its ability to change theta and land upright. Thanks for watching.